Hello. Yes, yes, I can hear you. Have you revised what we discussed last time? Any doubt in that hybridization? Any doubt in hybridization now? Any doubt in the topic of hybridization? Can you hear me? Hello. Can you hear me? Hello. Can you hear me? Okay. Do you have any doubt in the any topic of the previous that we have discussed? No doubt. So have you practiced question from the book? Okay. Any problem in it? Any doubt? Anything you want to ask? Okay. Okay. So now I'm talking about next topic, that is the dipole moment. Dipole moment. Okay. If I have an atom A and B, let it be like an HCl, out of the chlorine and hydrogen, which is more electronegative? Yeah. So that will be pulling electron cloud towards itself. And it will require partial negative charge, it will require partial positive charge. Right? So there's a polarity in the molecule. The molecule is now polar covalent bond. Polar covalent bond. It is a covalent bond, right? It's a polar, but the molecule is polar. There is a polarity, positive pole and a negative pole. Positive pole and negative pole, right? So there is a polar covalent bond. So greater the electronegativity difference between the two atoms, more is the polarity. Suppose I say the electronegativity of chlorine is 3 and hydrogen is 2.1. But if I talk about the HF molecule, the electronegativity is 4 and 2.1. It means in case of HF, there is a more difference in electronegativity. So there is a more polarity. It is more polar as compared to HCl. But yes, yes, yes. Right. So there should be some difference in the electronegativity. But if I talk about the methane molecule, if I talk about methane molecule, the electronegativity of carbon and hydrogen is same. There is no difference. So this molecule is non-polar. Polarity will come only due to difference in electronegativity. Am I clear? Any doubt till now? So there's a polarity. So how much electron has been displaced, that is determined in terms of the dipole moment. Dipole moment is denoted by symbol mu. How much polarity is there? Means if I say HF is more polar than HCl, so HF is more polar than HCl, then how much more polar? Quantitative aspect, right? So HF is more polar as compared to HCl. So I can say the dipole moment is like physical quantity to determine the polarity of the molecule. So dipole moment is equal to product of the magnitude of the charge that comes on these atoms, multiplied by the distance between two atoms. I can say bond length, D. Am I clear? The charge is measured in terms of electrostatic unit, 10 to the power minus 8 electrostatic unit. Charge is of the order of 10 to the power minus 8 electrostatic unit multiplied by D for distance, and that is measured in 10 to the power minus 10 centimeter. This is equal to now 10 to the power minus 18 electrostatic unit centimeter. And so it is equal to 1 dBi. 1 dBi is a unit of dipole moment. I said the magnitude of the charge is of the order of. This is the value of the charge. I said suppose I have a molecule of the HCl. How much charge is coming on the chlorine and how much charge is coming on the hydrogen? That will be equal. So whatever the charge is there, its magnitude will be positive only. Right? So wherever there is a difference in electronegativity, there is a polarity in the molecule. Okay, note it down this much. But I said the distance value or the order of the is equal to this much. Order is equal to this much. Okay. Suppose I say the HCl distance is 2.1 10 to the power minus 10 centimeter. What is the order here? Yeah. So that's what I said. The charge or distance value is or the order of 10 minus 10. Now, what is the effect of the dipole moment? First of all, let us see which molecules are polar. Suppose I have a molecule of HCl. There is a difference of electronegativity. The electrons will be more pulled towards chlorine. So dipole moment will be greater than 0 here. Getting me? Alright. I have a molecule like carbon dioxide, CO2 molecule. Oxygen is more electronegative than carbon. So electron will be pulled towards oxygen like this, like this. And there is a null vector operating over here. So dipole moment will be equal to 0. No, no, no. Null vector is operating. The pull is equal and opposite. Pull is equal and opposite. In this case, the dipole moment is toward this side. So dipole moment is equal to charge multiplied by the distance. It will come out to be greater than 0 only. Right? Understood? But in case of carbon dioxide, the pull is equal and opposite in both the direction. The pull is equal and opposite in both the direction. So dipole moment will be equal to 0 here. There is no net pull. There is no net polarity. Getting me? I will take up one more example here. Here carbon tetrachloride. Chlorine is more electronegative than carbon. Pulled toward this side, this side, this side, this side, all side. Right? So dipole moment will be again is equal to 0 because null vector is operating over here. Because null vector is operating over here. Am I clear? So those molecules which are symmetrical molecule. Sure, sure, sure. Okay. So those molecules which are symmetrical molecules, their dipole moment is equal to 0 and they are non-polar. I have molecule as a 1,2-dichloroethene. I have a molecule 1,2-dichloroethene. The chlorine is more electronegative than carbon. So dipole moment will be towards chlorine. Here dipole moment will be towards chlorine. Again you can see null vector operating over here. Have, right? Again the dipole moment will be equal to 0. But if you see this molecule, here the chlorine is pulling electron towards itself. Here chlorine is pulling electron towards itself. So upper part become partial negative and lower part become partial positive. right? The net dipole moment is upward and the dipole moment will be greater than 0. It's also 1,2-dichlorobenzene. But technically, with the two chlorine on the opposite side, we call this is a cis form of the 1,2-dichlorobenzene, and this is sorry. On the opposite side, it is called a trans form. Wait, this is a trans, and when on the same side, it is a cis form, cis 1,2-dichloroethene, cis 1,2-dichloroethene. Understood? Yes, Advait. Any doubt? You got it. Okay. Similarly, I have this molecule. It's a chlorobenzene dichlorobenzene, right? The dipole moment is upside this side, downside this side, and again dipole moment is equal to 0. But in case I have these chlorines at different angles, this way, and there is a angle difference of certain angle, let it be 60 degree here, theta angle. The net dipole moment will be in between the two. So in that case, you are done in the physics, right? How to find the net vector, resultant vector, right? So net dipole moment mu is equal to, suppose here mu is equal to mu1 from this side and mu2 from this side. So total mu will be equal to square root of mu1 square plus mu2 square plus 2 mu1 mu2 cos theta. Got it? So greater the theta value, lesser the dipole moment. Greater the theta value, lesser the dipole moment. So in case of this compound, here angle is of theta is equal to 60 degrees and here angle is of equal to 180 degrees, right? Just opposite. The greater the theta value, greater the angle, lesser the theta value. Understood? Now, if I talk about here ammonia, and I have molecule of NF3, ammonia and NF3. Nitrogen is more electronegative than hydrogen. So dipole moment will be towards nitrogen, right? And a dipole moment or lone pair is also on the upside. So net dipole moment will be in one direction, that is upside. The dipole moment due to the NH bond and a dipole moment due to the lone pair, they are on the same side, they will add up and a total dipole moment will be in one direction. Am I clear? But in case of the NF3 molecule, the fluorine is more electronegative than nitrogen, so dipole moment will be towards fluorine, and a dipole moment due to the lone pair is upside. It means they are basically acting opposite in direction. So that net dipole moment will be here in case of the NF3 will be less than that of the ammonia. They will be subtracting each other, right? The dipole moment of the NF bond minus the dipole moment of the lone pair. Here we are adding and here we are subtracting. It means the dipole moment of the NF3 is less than that of ammonia. It's a very good question, very important question. Question theoretically. Why out of these two molecules which has more dipole moment and why? It is given in anxiety question also. Next question. Should we go ahead? Hmm? That was the dipole moment. And now next topic is resonance. What is the name of this molecule? Benzene. And what is the name of this molecule? Same benzene. Do you find any difference here? Yeah. It means I can say there are carbon double bond in both the molecule. There's a carbon single in both the molecule. How many? Three double bond in both, three the single bond in both. If the molecule has double bond, the bond length should be 1.34 Armstrong in case of double bond and 1.54 Armstrong in case of single bond. It means bond length means the distance, this bond length, the distance here, right? Bond length. So bond length should be different. Double bond should have shorter bond length as compared to the single bond, right? Double bond brings the molecule closer, atoms closer, right? In case it is like this, then what will happen? Practically, we find that bond length in case of the benzene is neither equal to double bond nor equal to the triple bond, double single bond, but in between the two. It means both these structures are not matching, not in accordance with the experimental observation. These are our theoretical structures, and these are called as a canonical structures. Canonical or resonating structures. Or canonical or resonating structures. But what we find here is the bond length is in between the two. It is neither single bond nor double bond, but it has a 1.5 bond. So I can show it like this. This is the real structure of the benzene, and we call it's a resonance hybrid structure. Resonance hybrid structure. Am I clear? Yeah, these possible structures, these are A and B, these structures A and B. These structures are canonical structure. That is only according to our theory only. But experimentally observed is this one. A resonance hybrid structure is a real structure. So we call that this is a phenomenon known as a resonance. Write down resonance definition now. When two or more structures of a molecule cannot explain all the physical and chemical properties, but their hybrid can. It is called as a resonance. I'll do it. I'll discuss. Have you noted down? Now, here I have a carbonatine. I'll discuss how the resonance is formed. This is a carbonatine. I am drawing a Lewis dot structure first. But actually, this is not the carbonate structure. This is our theoretical structure. Okay. Now you can see that this lone pair and this pi electron are separated by single bond only. We say these are in conjugation. These are in conjugation. Yeah, that's it. They are separated by a double bond, separated by one single bond, separated by single bond. The lone pair and a bond pair here. Lone pair and this pi electron. This pi bond and this lone pair. They are separated by what? They are separated by what? Single bond. Then I say these are in conjugation. So this electron pair comes over here. If it makes a bond here, the carbon will start making 5 bonds, and that is not possible. Getting me? So what will happen? This bond will be broken and go here. Now this will become negative charge. This will become neutral now because it has lost one electron, and here there is no change. Done. Understood. See, if this pair that I'm highlighting now, yellow color, right, comes in between here, this carbon will start making 5 bonds. But carbon cannot make 5 bonds. So this pi electron will shift over to the next one. And so the oxygen will be getting negative now, and this oxygen will be not neutral. Right. So this electron comes over here. So this will shift now. So this will O will become negative. This become again negative. This become double bond. Understood? None of the structure is correct. Actually, the negative charge is dispersed all over. Done. Are you clear? Right. This is how we make the resonating structures. I have a molecule of the ozone here. This is one possible structure of ozone. The other possible structure of ozone is just opposite. These two are canonical or resonating structure, and this is a resonance hybrid structure. Understood? Right. This is how we draw the canonical structures. Any doubt? Should I go ahead? Okay. Now I'm discussing one topic, that is a hydrogen bonding. Other today evening, my 5:30 you will be available. Okay, means it will be your 4 o'clock, right? And I'm discussing hydrogen bonding now. And the evening time, I will be discussing with one last topic of this chapter, that is a molecular orbital theory, right? So just go through it, go through everything, discuss. You can discuss me all the doubts, all the questions of the NCRT. You can do it, right? If you're not asking me questions or doubt, then I will assume that you know, right? but practically, like in the exam, you will be able to write only when your all doubts and all questions are solved. Okay. Next, we have now hydrogen bonding. Consider this is a molecule of HF, right? Out of the fluorine and a hydrogen, fluorine is more electronegative. It is a partial negative charge, so it is a partial positive charge. So I can say the molecule has a dipole. It's a polar covalent molecule. Yes or no? Then I have again partial negative and a partial positive charge. Between two molecules, hydrogen atom of one molecule and electronegative element of another molecule, this bond is called as a hydrogen bond. This bond is called as a hydrogen bond, right? It's a partial negative and a partial positive. This interaction is a bond. This interaction is a bond. We call it is a hydrogen bond. Note it down. I'm not taking one. I'm taking one more example now. Any doubt till now? I'll explain this hydrogen bonding again. But in these structures, any doubt? No. I'm discussing here the water molecule. Water molecule like this. And out of the oxygen and hydrogen, which is more electronegative? Oxygen. So it is a partial and negative charge, and hydrogen has a partial positive charge. Right? Now I'm again drawing one more structure of the water molecule. It is again a polarity. Hydrogen atom of one molecule and electronegative element of the another molecule. This is one molecule, this is another molecule. Between the two, there is a bond that is called as a hydrogen bond. No, no, no. Water is a compound. Water is a compound. But in between two molecules of the water, there is a interaction, and this interaction is called as a hydrogen bond. Now, what is its application? Yeah, yeah. What will happen to the molecule? How will the property change? That I'll discuss. But first of all, let me explain what is hydrogen bond. Then we'll come to the its application. That will make it more clear. What is this molecule now? Right, ammonia molecule, right? Out of the nitrogen and hydrogen, which is more electronegative? Nitrogen. So it is a partial negative, and hydrogen has a partial positive charge, right? It's a polar molecule. Now I'm writing here another molecule of ammonia here. Partial negative and a partial positive. Between these two molecules, hydrogen atom of one molecule and electronegative element of another molecule. This bond is again called as a hydrogen bond, right? I had defined hydrogen bond in three different examples. Now, hydrogen must be bonded with the fluorine or oxygen or nitrogen, then only hydrogen bonding can be considered, or we can call between two molecules there is a hydrogen bond. But in case I have an HCl, Here also I have here also I have polarity. But here I will not call this interaction as a hydrogen bonding, but this interaction will be called as a dipole or dipole interaction, because dipole is here, so dipole dipole interaction. Hydrogen bonding will be called only when hydrogen is bonded with the fluorine, oxygen, and nitrogen. Only in this case only, not in any other case. Understood? Okay, wait. First of all, understand the first example of hydrogen bonding that I have given here between two HF molecule. So this hydrogen is bonded to the fluorine, then only it can show the further hydrogen bonding. This hydrogen bonded with oxygen, then only it can show hydrogen bonding. The second case, in case of the water, is that clear? In the third case, the hydrogen is bonded with the nitrogen, then only it can show the hydrogen bonding. It means hydrogen must be bonded with the high fluorine, oxygen, or nitrogen. Then only they can show hydrogen bonding. But here hydrogen bonded with what? Chlorine. So even though the molecule has a polarity, but the bond between two molecules will not be called as a hydrogen bond, but that will be called as a dipole dipole interaction. Yes, only when the hydrogen is bonded with oxygen, nitrogen, and fluorine. Yeah, in case the molecule is polar. In case the molecule is polar. I hope it's clear, right? So when the hydrogen bonding is a bit dipole dipole interaction, dipole dipole interaction, dipole dipole interactions. Done. Right. The hydrogen bonding that I have shown here, the hydrogen bonding that I have shown here between two molecules, then the bonding is called as a intermolecular hydrogen bonding. Intermolecular hydrogen bonding. That is between two molecules, like I have shown here between the HF and HF, or in case of the water and water, or in case of two ammonia molecules. So that interaction is called as a what? Intermolecular hydrogen bonding between two molecules. Am I clear? Now I have an example of this is called as a phenol, and at this position, if I put here nitro group, this hydrogen and oxygen bond here, again it's a hydrogen bond, but it is within the same molecule, so we call this is a intramolecular hydrogen bonding. Intramolecular molecular hydrogen bonding. Intramolecular means within the same molecule. Right? Note it down. I can give one more example here, the intramolecular hydrogen bonding. This is, I have a molecule of OH here and COOH here. This interaction within the same molecule, so we call it say intramolecular hydrogen bonding. Understood? Now, orthonitrophenol, that compound is called as a orthonitrophenol. This compound is called as a orthonitrophenol. Orthonitrophenol. My question is now another case I have. If I put here at this position, then we call this is a paranitrophenol. Understood? I'll not tell you. If I say I had now another molecule now, this is also paranitrophenol, right? Between these two molecules, there is a intermolecular hydrogen bonding. Can you see that? Intermolecular hydrogen bonding. In case of paranitrophenol, there is a intermolecular hydrogen bonding, right? But in case of the orthonitrophenol, there is a intramolecular hydrogen bonding. This is the orthonitrophenol. And here this interaction is a intramolecular hydrogen bonding, right? Understood? Now, if I had this with one molecule and similar type of molecule is here, means one more orthonitrophenol in its vicinity, there must be some interaction between the two molecules, but that is not due to the hydrogen bonding. This is just a very, very weak force of attraction. We call it is a weak van der Waal force of attraction. Weak van der Waal force of attraction. Okay. Out of the hydrogen bonding and van der Waal, hydrogen bonding is always strong. And that is why the boiling point of Paranitrophenol is more than, greater than that of the orthonitrophenol. Is always greater than that of the phenol. Understood? Right. So I can say now I'm telling you the application of the hydrogen bonding. In case between the two molecules there is a intermolecular hydrogen bonding, and here between the two molecules there is a weak van der Waal. Hydrogen bonding is stronger. Hydrogen bonding is stronger, and that is why paranitrophenol has a higher boiling point as compared to orthonitrophenol. Understood. Similarly, if I talk about I have water and H2S, between two molecules of the water, what type of hydrogen bond, what type of bonding is there? What is this bond between two molecules? Hydrogen bonding. And here also I have an H2S. Now between two molecules of H2S, what type of interaction is possible? Wait. Between two molecules of H2S, what type of interaction is possible? Is it hydrogen bonding? But still it has some polarity, right? I can some dipole-dipole interaction is there. Outer dipole-dipole and hydrogen bonding is stronger. That is why this water is a liquid at room temperature, but H2S is a gas. Because interaction among the water molecule is more stronger as compared to H2S. As compared to H2S. Got it now? Any doubt till now? Right. So Advait, I'm ending the session now, right? And now see you in the evening time. Your 4 o'clock might 5:30, right? Note down all these things, revise it, and solve the question given at the back of the book, NCERT book, right? Okay, then. See you in the evening. Bye for now.